Hey guys, welcome to my tutorial from GoRobot, and today I will talk about the PID Linefollower. And to begin with, I will show you how the simplest of all Linefollower would actually work. So you have a robot, and this robot should have one light sensor or color sensor, and it can detect the value of the light which gets reflected back to the sensor. So for example, if the sensor is on this black line, it would receive a value of 0. And if it's on the white, it would receive a value of 100. And if it's perfectly on the edge, it would receive a value of 50. So now we have to program a program which lets the robot decide which actions to do depending on which values it gets from its color sensor. So the basic idea of the Linefollower is that you actually want to follow the edge of the line, because if you don't know which side to go. So for example, if your robot detects black and it drives forward, but then it detects white, it doesn't know if it's on this side or if it's on this side. So you have to follow the edge, because then you only have one black side and one white side and all values in between. And how you do this is just you have a switch in which you decide if it's less than 50, then turn to the right, and if the value received is bigger than 50, so it's on the white side, then turn to the left. And you can try to make it if you want. I am now not going to show you how to do this, because the problem with the system is that the correction or the turn value of your motors will just have two states. It can only drive to the right or it can drive to the left. So your robot will drive in the zigzag. It will look like this. So it detects black. Okay, now move to the right. Then it sees white and it will move to the left again. And this goes on forever until you say it to stop. So as you can see, the robot doesn't follow the edge of the line very smoothly. So you have to do something. One option that you have is that you add another states. For example, if your sensor is like this, you get the value 25, for example. And then you can say, if it's less than 25, drive hard to the right. But if it's less than 50, but bigger than 25, drive to the right, but not as hard as if it's less than 25. And same on the other side. If the value is 75 in this case, and then the correction shouldn't be minus 50 like if it's bigger than 75, but it should be, let's say, minus 25. So the correction is minus 25. So it drives with the value of 25 to the left. Here it drives with the value of 25 to the right. So correction is 25. And now what this makes is that it doesn't only have two states, it will have 4 states. So it will drive like this, then your sensor recognizes, oh, it's the value received by the color sensor is now less than 25, so let's make the correction a bit smoother. So as you see, your robot will follow the line a bit smoother. So it will follow it like this. First it will go hard, and then a bit smoother, and then hard again, and a bit smoother, so it will eventually follow the line better. But you can even improve this even more. So let's, for example, add another value, 30. So if it's even more to the right, then the correction should be less. Let's say the correction now is 20. And as you can see, the more the robot comes to the edge, the less the correction gets. So this is what we actually want to have the curve. So we can achieve this by the proportional controller. And what it actually does is it takes the value by the color sensor and measures, or yes, it computes the distance between your sensor and the edge of the line. So for example, here it's 0. So the distance of your position and your position where you want to go is really high, so it has to turn more. And if it's here, it doesn't have to turn anymore because the distance is 0. So it just calculates the distance, and with this distance it will calculate the error, so or the correction. And the distance that is from your color sensor and the edge of the line is called the error. So error equals your the distance between your actual position and the offset. So here this edge of the line is called the offset, where you want to go. So, or offsets minus the value of your light sensor. And that's just the error. And now you have to have the correction. And for now, let's say correction equals error. And implement this in our EV3. So we put a loop here, measure the light value of our color sensor, and do a little bit of math now. Okay, so we have now our light value and we need now our offset. The best way to do this is, let's put here a constant. So the offset is variable. So it's actually a constant, but the darker your line gets, the lesser the offset is. So you have to change it depending on how dark your line is. And if you do it like this with a constant, you can change it pretty easily without having to change it inside here. Just do it because it's better. And now we have to calculate our error. And oops, we do it just like this. Okay. So, oh, sorry guys, I have made a mistake, because actually it's the sensor value minus the offset, not the offset minus the central value. But it actually doesn't matter, but it will matter if you want to change the size of the line which your robot has to follow. And now what we have to do now is set the value of the offset to 50. Maybe the value of your offset will be different, but ours is 50. So now we have this error, and we have to calculate the correction. But actually what we have said was that the correction equals the error, so just multiply it by 1. Maybe we will change it later, so leave it just like that. And what we have to do now is pass this correction value to the motors. And how we do it is we let one motor drive by a value which gets changed positive by this correction value, and the other gets changed negative by this correction value. So for example, here the correction value is minus 25, so the one motor has to drive by, for example, 25, and the other has to drive by minus 25. And if it's the positive value, it has to be the other way around. So one way to do this is that the power 1 from one motor equals the correction, and the second motor is the negative value of the correction, so minus correction, and that would actually do just what I told you. So let's say the correction value is minus 25, so the first motor will turn with the speed of minus 25, so it will go backwards, and the second will go forward, so it will turn to the left. That's actually what we wanted to do. But the problem is that we can't change the speed because it's always 25 if this is 75. But maybe we want the robot to go faster if it's exactly on this position. So we add a speed value. And that's actually how we compute, or how we compute our powers for our motors. So let's add the speed constant again, which you can change if you want it to be faster or slower. Let's tell it to drive with a speed of 10. Then do what I did here, correction plus speed. So that's the correction. And the first power is the speed plus the correction. The other power for the second motor should be the speed minus the correction, because if we swap those two things, it will look like, the formula would look like this: speed minus the correction. It's just simple math. So let's put this to minus and add the speed, and the correction value. Now we have to pass these values to the motors. So one motor is B, and the other motor is C. Maybe you have different ports, so change it so that your ports are right. Okay, so now test it. I will test it too. And it works fine. But what you may have seen is that the robot still does the zigzag move. And that's because our correction value is -25 if it's here. And it actually didn't make almost no change to the basic line follower, only that it's proportional now. So what we want to do now is we want to be able to switch this correction value. And we can do this by adding just another constant. So we say the correction value is the error times the constant of the proportional. Okay, so if we make the constant higher, the robots will follow the line more rapidly or more like a zigzag, and if we make it smaller, it will follow the lines more smoothly. So here we can change this value, and I will do this with the constant again, so it will be easier to change. Okay. Now let's change this to 0.5 and test it out again. Okay, well, it now works perfectly fine, and the robot follows the line very smoothly. If you want the robot to move faster, you can change this value, for example, to 50 or whatever you want. And if you want to the robot to make smaller curves or tighter curves, you can change this value too. Just experiment, pause this video and experiment with the values, so have fun. So have you finished experimenting now? If yes, then let's go on and clean or make our project cleaner so that we can modify it easier in the future. So add a variable, make a new variable with the names KB for proportional constant, and feed the value of a proportional constant value inside the variable. And then feed the variable to the equation. Okay, and then what we're going to do now is moving the speed into a variable too, so we don't have all those strings going all over the place because it doesn't look very nice. Okay, and then we have to feed the variable back into the equation too. Okay, if you want, you can try it now, compile and run it. But right now, I don't want to do it because I'm lazy. So let's go on and add the integral. So what is the integral? You can call the integral the memory of the controller, because what it basically does is it summarizes all the past errors. So, for example, if your first error was 50 because your light sensor was on the black line, your integral gets 50 because 0 plus 50 is 50. Then, because of the correction, your robot drives to the right. Then it's, for example, 30. So your integral gets 80. And this just goes along until your robot stops line following. And what that does is it will correct past errors, because as you have seen, the longer the robot stays on one side, the higher the integral pushes your robot to the other side, because the new correction will get the integral added, and the integral is multiplied by a constant just like the error. What that does is, if you switch it correctly, you can prevent your integral from overshooting, because as I've told you, your integral gets higher and higher the longer you stay on this side. So let's say the integral here is now 0, and then 50, 80, and it gets higher and higher until your actual error is 0. So what your robot would do now is it should actually drive forward, but because of the integral, if you switch it badly, your integral will be like 500 anything, and it will push the robot furthermore to this side, because it has thought that well, the robot was too long on this side, so it will have to push an extra bit more. But the thing is, because the error is already 0, you don't want your robot to be pushed so hard by the integral. So you need the constant integral to twitch your integral so that it gets lower. And I've already implemented the math here. Here I will show you. So you need a variable which is named integral and initialize it at 0. What you also need is the constant integral and set it to a low number. But if you want your robot to be more accurate, you can make it higher, but it will overshoot more. Then add your current error to your integral by just reading out your integral and adding your error and feeding the value back to the new integral. Then you have to multiply your integral by your constant integral, and then add this to your initial correction which you had before, and then just compile it and run it, test it, and try to get the best value for your constant integral. Well, let's move on to the last missing part of the PID Linefollower. It's the derivative, and what it does is it predicts the next error by measuring the difference between the current error and the last error. So, for example, now the derivative is minus 10, and because this difference is minus 10, or this difference is 10, the next error might be the current error minus 10, as you see, because the graph moved like this, and it will probably not change much, so the derivative can predict the future by just measuring this difference, and then he knows what approximately the next error will be. And what that will do is that it will that he can correct the next error, because maybe it will overshoot, and this will cause a zigzag move again. And what it can do is it can smoothen the move to the line, so that you won't have this zigzag move again. So that's the equation. Derivative is the error minus the last error, and you have to add the derivative to the correction, but multiply it with a constant again. I've written this wrongly. This is the KD, constant derivative. And well, let's add this to our EV3 project. What we need is a variable which name is last error, so we can save the current error to the last error. So every time the loop finishes, you will have to save the current error to the last error. So just put this right in here. And save your error into the last error. What we also need is the constant derivative. So just copy and paste this over here, change the variable name and the value. This value can be high if you want. I prefer high values for the KD because what it does is it makes your line following pretty smooth, and for the FLL it is pretty recommended, so that your robot won't wiggle that much. Then what you also have to calculate now is the derivative. So the derivative equals error times last error. So let's put our math block in here. set this to minus, and we have to read our last error. Then put the error on the left side, and the last error to the right side, so that it gets subtracted from the error. And the output value that gets outputted from this math block is the derivative. And what we have to do now is we have to add the derivative to the correction. But because this math block is already full, we will just add another advanced math block behind it. Okay, and let's add the derivative. Oops. Finally. And we have to multiply the derivative with the constant derivative, so the KD. Okay, and now this is the new correction value. So throw the old ones away. And now add the new correction value to the equation for the power. Alright, and that should be it. Now you just have to compile and run it and experiment which values for your constants would fit the best. And what you can also do is you can add everything to a my block and do some changes. So our my block looks like this. It has a light value as input, which is the offset. Then we have the speed, the Kp, Ki, and Kd. We have the following port for the sensor which follows the line, and the trigger port to stop the robot if it detects a line. If this is set to 0, we also have a distance measure, so the robot will stop after a certain distance. And we have the trigger value for the trigger port, which is the light value where the robot has to stop. And we have a logic variable where you can set whether you want to drive on the left side or on the right side of the line. And this is how our my block looks like. So if you want, you can do this too.